everybody, welcome to MSDOSX lecture number 5. This will be split up, 3 quarters and a quarter, something like that. First part will be UI design principles, and the second part will be debugging and talking some more in depth about debugging. We'll do optimization and things later on down the road using instruments. But we'll do some just common Xcode debugging techniques. Should help you out with your projects and labs.
Okay, but the bulk of today's lecture is going to be fairly non-technical. It's just sort of a we've got feedback in the past of people who wanted, before we actually started designing UIs in Mac and iOS, to kind of just have some sort of more 5 miles up of how you design a user interface and kind of what the process is and kind of just some principles of how to design interfaces. So this lecture is very heavily influenced by CS160. A lot of these slides I took right out of Professor Hartman's slides, so credit to him for a lot of these. So let's get started. If my clicker wants to go. Of course it won't. Oh, now it goes. Okay, so the crux of modern user interface design is a broader concept of what's called human-computer interaction. And there's obviously 3 parts to it. There's the computer, which is the machine your application is running on. These days, that's often split between a client and a server. So there's some server up in the cloud that's got a bunch of data, and it has a bunch of quick accesses to all that data. And then there's a light client on your phone or your laptop or your iPad that talks to that server and gets some data. So the computer now is a little bit more of a vague concept, but we all know what a computer is. It's where your application is going to be running. On the other side, of course, we have the human. This is who's using your application. And one really important thing to remember when you're designing user interfaces is that the user of your application is somebody else. You have to design it so that somebody else knows how to use your application. If you design it just so that you know how to use it, that's great, you know how to use it, but it's not likely to be usable by somebody else. And then, of course, HCI there's an interaction between the human and the computer. That's how the computer gives instructions, the user gives instructions to the computer, and the computer gives back a response to those instructions. So before we get started, I wanted to ask you guys, what to you is a user interface? Does anybody have something they want? What's a user interface to them? Anybody? Come on, you all know what a user interface is. You use them all the time. What is a user interface? Nobody wants to answer? You guys are quiet. Okay, so the basic part of a user interface is it's the specific part of your application where the user tells the computer what they want to have happen, and where the computer tells the user, hey, I'm done with this computation, here's the result you get. And we often think of the user interface as just being the display, but really there's a lot more to user interfaces, especially now that mobile devices are becoming more popular. We have, for example, accelerometers, we have gyroscopes, we have physical switches, and we have physical buttons and other sensors like cameras and GPS. Those are all part of the user interface. And so when you're designing, especially a mobile app, it's important to think about not just the display and not just all the buttons and things on the display, but also all the other hardware aspects of the device you're working with. So the whole point of user interface design is to make a user interface that's usable. And what does it mean for something to be usable? And there's some basic core concept of usability that HCI have defined. And the first is that it's easy to learn. It's fine for some new application to be hard to use the first time, but the more you use it, the better you should be able to get at it. And there should be a learning curve that's not too terribly steep. That the more you use it, the better you get at it. There's a distinction between what's called remember and recall. Remember is basically that the application reminds you how to do something in case you've forgotten, whereas recall, it requires you to recall from memory how to do something. The traditional Unix prompt, for example, doesn't really give you hints on how to use it very well unless you remember the names of all the different programs like find and all those other programs. So that's a recall user interface, and arguably it's not very good because it requires you to remember all these different programs that your command line can use. Whereas the modern GUI, where you have application icons, where there's a little picture of all the applications, it reminds you, oh, this application is the media player. Oh, this application is the photo viewer. So you want to minimize the amount of recall that you require of your users, so that way they can just take a quick glance at your application and remember how to use it. Applications should allow the user to be productive. They should let them do something, and whenever possible, it should be. You want to try to minimize the amount of error that the user can make, and if they do make an error, you want to minimize the impact of that error. If a user can accidentally delete a file, and you want to make sure that they know that they might delete a file. So that's why there's often confirm dialogues for things like deleting a file, so that way you make sure, actually, yes, I do in fact want to delete this, and I didn't just accidentally press the delete key. And they should make your users happy. That's kind of the last important bit of usability, is that the user should enjoy using your application. If your application is not fun to use and it's a pain to use, then they're not going to use it very often, if at all. So if there's one slide to remember from this lecture, it's this one. This is a really the core concept of user interface design is that it's this iterative cycle where you have a design in mind, you make a prototype of the design, you test the design, and then you evaluate how good that design is, and then you redesign it, and then you reprototype, and then you retest, and then you redesign and reprototype and retest, and you do this until you run out of time or money. Really, that's how good interfaces are designed, because interfaces are very hard to get right the first time. They're really hard to get right the first time, and you usually won't. So the more times you just design something, make a quick prototype, test it with some people, get some evaluation back on that, redesign it, refine your design, and keep getting more and more sophisticated with your prototypes, and eventually you'll have a fairly usable application. So just to go into a little bit of detail about each of these phases, the design often starts with a process that's called task analysis or contextual inquiry, where you have some goal of some application or some group of users that you want to help make their lives better, and you observe them, see what they do currently, see what they struggle with, see what works really well right now, and this will allow you to kind of refine your goal and figure out what your service needs to do. If, for example, you are writing an application to help BART riders, go to a BART station, watch BART riders buy tickets, go through the fare gates, run to their trains, things like that. So that way you can actually see how the users currently do what they're doing, so that way you can get a sense of what needs to be improved and how you can make it better. The important thing about this is that you shouldn't guess. You don't know everything, and you don't know all of your users, and users are different. All the users aren't going to be the same. So if you observe real people doing things, then you'll get a better sense of what actually they need. And ask them questions. Watch them do real things. Ask them questions. Ask them what they think is hard. Ask them what they like about the current interface or whatever it is you're interested in. So then the next phase, once you've sort of got a design in mind, is you build prototypes of your idea. And the idea is that the more times you go through the cycle, the more sophisticated your prototypes become. But at the beginning, they're literally just on paper. They should literally just be on paper, using Post-it notes to kind of get the different pieces of your application to move around. So yeah, like I said, really low fidelity, because the benefit of doing things on paper is you can do it really fast and really inexpensively. Writing a full-blown application is a lot of work, and if you write an application and discover that the user interface is terrible, then you've wasted a lot of hours writing all this code. Whereas if you just run it out on paper and kind of had a person just tap on the different sections and then show them new screens as things change, or add pop-up menus or remove pop-up menus using like Post-it notes. Obviously, it won't look very pretty, but early on, the point is more to get the interaction correct, and then you can make it prettier and prettier the more you work with it. But getting the interaction of what leads to what and what different buttons actions do is important to get early, and doing things on paper allows you to do it very, very quickly. And then maybe after you've done a few iterations of doing it on paper and you have a design that you think is good, you do some sort of more medium-level interactive prototype, doing things in HTML and CSS, and maybe some JavaScript, maybe some Flash or some Visual Basic, just something that's not quite so work-intensive as a full-blown application in Java or C or whatever. but is a bit more finished looking than on paper. And then by the end, you're writing a full application using Interface Builder, which is a tool we'll talk about in a few weeks about how to build actual user interfaces in iOS and Mac. Visual Studio if you're doing a C or C++ program or a C# or a Windows program, and things like Java, like full-on Java applets. But the idea is that you don't get to those until you've done a lot of design work, so that way you can work out most of the bugs in your initial design. So that way you don't have to keep recoding your application every time you discover a problem with it. You can just fix a lot of the big errors early and just kind of tweak some of the minor mistakes later on. And then the last phase is the evaluation phase, and there's a couple ways to do it. One is, there's sort of two main ways to do it. You can either do it totally analytically without any users. You get maybe an expert to kind of just look at your app, know some rules of thumb and some guidelines of what works in the past and what doesn't work, and they'll kind of give you a score of how well they think different parts of it work. And then on the other side is to actually test it with real users. And this can go anywhere from a quick test where you just go to your roommate and say, here's a stack of paper, press a button, and then I'll switch the paper for you, and then that kind of thing. Or you have a full-on fancy controlled user study where they're in a test chamber and you have cameras and all this kind of stuff. The Microsoft approach to writing software. It's worth noting that Apple doesn't do user studies.
I try.
Yeah. The user interface design design model is useful to compare to the typical software engineering model, which is often called the waterfall model, which is a process where you start with some description of what your application should do. You do some analysis of that description, and you use that to define a specification for your application. Then you design it. Then you come up with a design for this system. Then you implement it and have a finished product. Why isn't this ideal for user interfaces? Does anybody have a guess? An idea why this might be a bad idea for designing user-facing applications? What's missing from the software model?
It's not type-driven.
There's no feedback, right? You better hope you did it right in the first place, because once you get to the bottom, you can't really make any changes. So one of the really useful things about the iterative cycle is that you have feedback constantly. Ideally, those cycles are really short, like a couple of days or a week at most. You just keep churning on the same idea, and then you fix bugs. Another flaw with the waterfall model is that the further into development you get, if you discover there's a problem, it becomes orders of magnitude more expensive to fix, say, down in system design than when you first started. And so that's inadvisable for something like user interface design because it's very hard to get it right in the first place. So you want to, for things that are hard, you want to fix the big problems early and the small problems later. And sometimes when you're designing something with the waterfall model, you don't discover big problems until it's too late. Whereas if you do this quick cycle of rapid prototyping, you'll discover a lot of big errors really early and then save you a lot of time and money. Okay, so that's kind of the basics of HCI. That's kind of, I think, the first 2 weeks of 160 in 10 minutes. So for the rest of this time that I have, I'm going to talk about some general user interface. I put UI in parentheses because these are really just broader design principles of really you can think of anything. This is adapted very heavily from a book called The Design of Everyday Things by Don Norman, who is a psychologist who used to be at UCSD, and I forget where he is now, but he wrote this really great book about why we put up with, or why we shouldn't put up with badly designed objects, like doors, or really simple, ordinary objects that don't need to be designed poorly, and he gives some principles of what makes a good design in a physical item. And a lot of these principles, and almost all of these principles, apply when designing a user interface. His first main principle is make things visible. So this is, I think, a nuclear power station. What's really good about this interface? There's a knob and a switch and a meter for everything. So you can see, the layperson will have no idea what any of them mean, but there's a switch for everything. You can see everything about the system. So it's very clear what state the system is in. and how to, and if you need to make a change to the system, it's pretty clear there's at least a button for being able to do that. So as he puts it, the correct parts must be visible, and they must convey the correct message. So there should be a control for everything, and it should be very clear how that control works. The other line that I really like is when the number of functions exceeds the number of controls you have, your design suddenly becomes arbitrary, because how do you decide to do 5 things with 3 buttons? You can certainly do 3 things with 3 buttons really easily, because there's just 1 button for each thing. But if you want to do 5 things with 3 buttons, how do you tell the user, okay, if you want to do thing number 4, then you press these 2 buttons, but if you want to do thing number 5, then you press these 2 buttons? There's no real natural way to choose what those additional functions mean. So that's why he says that becomes arbitrary when you have more functions than you have controls. And this is why you'll find that sometimes things are hard to use if there's more functions than there are controls. You have to remember how to use these specialized controls. Another principle that he points out is to establish a clear mapping. So does anybody know what this is? Yeah, it's a controller for your car seat. And how do we know that? It looks like a car seat, right? It's got the same shape as a car seat. How do we use this to move the seat?
Yeah, basically knobs.
Yeah, you do exactly to this what you want to do to the real seat. If you want the seat bottom to go forward, you push the seat bottom forward. If you want the seat back to tilt back, you tilt it back. So there's a one-to-one mapping between what the controls do and what it does to the actual thing. So here's a little exercise that we'll do in establishing mappings. So suppose we're designing a stovetop. We have 4 burners arranged in a square like this, and we have 4 controls arranged in a line along the bottom. Can you tell me which knob controls which burner? No, right? If I really wanted, the leftmost knob could control the upper right burner, or whatever we wanted. There's no clear mapping between which knob controls what button. So if somebody designs one like this, they probably have little labels on each of these. But what happens if you scrape off the labels? Then you don't know which one is which. So here's a slightly better solution. We kind of visually split the knobs into 2 halves. So why is this better? We know this very subtly tells us that these 2 knobs on the left control the 2 burners on the left, and the 2 knobs on the right control the 2 burners on the right. But it's still arbitrary because we don't know which is which. How about this? This is a slightly better. This is even better because now there's a clear left to rightness of the burners. There's a very clear left to right ordering of the burners that maps onto the left to rightness of the knobs. So now I don't need labels on the knobs to say which burner is which, because it makes sense based on the left to rightness of them. Here is arguably an even better way, because here we have the knobs in the exact same configuration as the burners. So again, we don't need labels because the mapping is clear. Does that make sense? Okay, and his third principle is give feedback. And this picture is actually generally an example of bad feedback. How many people, when they press the crosswalk button, press it more than once? Pretty much all of us, right? It's when you press that button, how can you be sure that the light heard you? How do you know that the light knows that you want to cross the street? So you'll press it more than once just to make sure that it got it. And the reason we feel the need to do that is because often these don't tell us that we've pressed the button or that it's acknowledged it. Newer ones do actually beep now that when you press the button, but it used to be that they didn't beep. So you wouldn't know if you press the button.
My personal favorite example of this, I forget where, but I've encountered several crosswalk buttons that when you push them say, wait, wait, wait. So
yeah, those obnoxious ones that they have in like airports that tell you to wait while it's going.
They're like, have patience, stop pushing me, go away.
Yeah, I think there are some in England where like the sign on the opposite side of the street that says wait or don't wait or wait or walk, it will actually change when you press the button to something like to in some way acknowledge that you pressed the button and tell you, okay, you're going to get to go soon. And then it will say go, and it's actually your turn. So it's very important to give feedback, because if you don't give feedback, then your user tries to do something, and they don't know if it worked. So they don't know they'll press that button 50 times, and if you don't want them to press the button 50 times, then you failed, because you need to make sure that they know when you press a button that something happens. A great example of feedback is the telephone, and I don't mean your cell phone, I mean an actual phone that's plugged into a wire into the wall. The original phone, one of the things that it had is phones have a dial tone. What's useful about a dial tone? It tells you that the phone's connected. If you don't have a dial tone and you pick up the phone, would you know if it's connected or not? Not really. But if you have a dial tone, you're like, okay, I know the phone's connected. I know that I can actually call a number. Old phones used to, and maybe they do. I think they still do, but cell phones do this not very well, where the voice of the user will actually be fed back into the earpiece, so that way the user can know that their voice is being picked up by the microphone.
That's why you hear a lot of people yelling into their cell phone when they talk regularly on a landline.
Because they can't be sure that the phone is hearing them. Okay, so those principles, they seem obvious, right? It's like they seem like things you should always do, but as you can see, there are numerous examples throughout our world that don't follow these principles, and those things are hard to use. An example that he brings up a lot in the book about bad mappings are like faucets or shower controls. For example, a shower control, there's basically two things you want to be able to control. You want to be able to control the temperature and the amount of flow. And it's often the case that there's just a linear control. It's not clear what does what, or if there's not really a left to rightness of hot versus cold. There's sort of a standardization that left is hot and right is cold. But what some designers will take that and make it vertical, and then it's not clear whether hot is down or up or. It's a really great book if you get the chance to read it. I really enjoyed it. I meant to bring it today, but I forgot. But he has just so many examples of things that are very badly designed, and now every time I see something that's badly designed, I'm like, oh, Norman. Because there's a lot of things that are very poorly designed that don't need to be. The other example that he brings up a lot are doors. And he brings up doors a lot because doors often have signs that say push or pull on one side, right? Why do we need those? If you design the door right, you don't need to tell the user to push or pull. If you have a big bar on the door that's aligned, that's pretty clear that you need to push it. If you make sure that it's all on the side where not away from the hinge, they know which side of the door to push it on. So he makes there's this really great story in the book about a friend of his that went to this fancy post office in Europe or something that had two rows of glass doors that had no handles, no visible hinges, and he went in the one door, he was fine, and then he kind of turned away and unknowingly shifted to the side before he got to the second side of the door, pushed in the door, and it wouldn't go, and he was like flustered that he couldn't get to the door, and then he went back and he couldn't get out the other side. And he was like trapped because he couldn't see where the hinges are. It's a really great story, but it brings out the point that things should be mapped well and that things should be visible. So those are really useful concepts in designing ordinary objects, but also in designing interfaces. That you should have a control visible for everything you want your application to do. That you should have a clear map between what the control does and what the control controls, and that you should have feedback for when you do something. Okay, so the next thing I want to talk about is the idea of a conceptual model. One thing that humans are so good at that we don't even really realize we do it is that we are constantly forming mental models of how things work, especially when these things are complex and things that we can't fully understand. Like, sure, if you take 61C, you can know all the way to the ground how your compiler works. You probably don't want to know that all the time. So you form a simplified mental model of what it does, so that way you can kind of get a general sense, you can kind of speak about what it does without really knowing the internals of it. And this is both a blessing and a curse. It's great because it allows your user to figure out what to do without really knowing exactly how every piece of it works. It's a curse in the sense that if the user forms the wrong model, they're going to get very frustrated by your application because they're going to try to they think they know what they're doing. They try to do it, and then your application responds in a way that's different than what they expect. And so they'll keep trying it and not understand why it's not working. So it's really important to encourage your user to form a mental model that matches what you actually are doing in the application. And at times it's harder to do than you think. But if what the user's actions, if they expect what the actions actually do, then it's going to be a lot easier for them to use, and they're going to be a lot happier with the application. So this is a diagram that I lifted from the Norman book, where this is us on the designer on the left-hand side, and then on the right-hand side we have the user, and in the middle we have what he calls the system image. The idea of the system image is that's what the user sees of your system. So in the case of an application, that's its user interface. So we certainly can influence the system image because we can manipulate everything about the interface that we want. The user can't talk to us to ask us how to do things. They only can determine what to do based on what they see in the system image. So it's important to make sure that these match as best as possible, so that way they know how to use your application. And again, it's important to remember that your user doesn't work with you, they work with the finished application. And so the finished application needs to be able to tell you what to do with it. Going along with the idea of of conceptual models is a notion that Norman introduces that he calls an affordance. It's the idea of the perceived and actual properties of something, especially those that influence the idea, that give you an idea of how the thing is supposed to be used. Which sounds like a big formal gobbledygook example, a bunch of fancy tiny words, but it's really just an affordance is when you look at something, what it tells you about how to use that thing. So things like knobs you can afford turning because they spin. Buttons afford being pushed. Things like glass can be seen through, and these are kind of things that these objects afford these actions. So the idea is that they give clues as to how the thing is supposed to work. So what's this on the left here? This is a car door handle, right? What affordances does this door handle give? Well, one that I see is there's sort of this pocket back here, and that to me that affords putting your fingers in there, which tells us that the way this works is you pull out on the handle. Another affordance is that there's what appears to be a hinge on the left-hand side, so we know that when we pull it, it's going to turn toward the left. There's also there's a lot in here, but you can also say there's this little switch here, there's little knobs there's little ridges on here to tell you that this is something that you can adjust and move, and that will lock the door. What affordances do scissors have? Anybody? There's two hole sizes. In particular, there's holes, and holes where your fingers can go. But this particular pair of scissors has two different size holes, so those indicate two different sets of fingers to put in those holes. You could, if you really wanted, you could put your thumb in the large hole and everything else in the small hole, but that'd be really hard to use. Scissors afford cutting because they have sharp blades. So does the idea of an affordance make sense to everybody? It's kind of just clues as to how the thing works. So now, speaking more about user interfaces in computers, what do screen-based what does a screen interface afford? The screen, it's got a pointing device, it's got a mouse or a trackpad or something. The keyboard has physical buttons, there's physical buttons on the computer. Generally speaking, these will afford things like clicking, touching, pointing on every pixel on the screen. And really, until recently, we haven't really leveraged the touching. But as touchscreens become more and more popular, we're really taking advantage of the fact that a screen wants to be touched, and that's, as we've seen the prevalence of touchscreen phones and touchscreen tablets, that's a popular notion because it's, there's a thing on every point on the screen, so why can't I touch it? So here are some example UI widgets from Mac and from iPhone. So let's kind of does anybody want to give me an example of an affordance that any one of these has? What about this one? What affordances does this have? It's clickable, right? It's got some shading to kind of give the illusion that it's popping out of the screen, which means you can press it. How about this? The little magnifying glass tells us that this does a search of some kind, and there's enough space for you to type some text, so you can type into that. How about this one here? It's a slider. This looks like something you can grab and just drag left to right to kind of slide and adjust some value left to right. We got a couple of similar ones over here. This top one on the right from iOS, what is that? What affordances does that give? It's like a switch. It's an on-off switch. You can drag it back and forth to turn something on or off. And one sort of interesting thing about graphical displays is that, in terms of affordances, is that a little bit of graphic design goes a very long way. These two are pretty much the same shape, right? They're kind of just this kind of pill-shaped oval. But which one's more obviously a button? The one on the left, right? This, sure, I could make this a button if I wanted, but it's flat. It doesn't really have any shadow or shine, so it doesn't appear to be stuck to the screen. It looks like it's just part of the display, whereas this button looks like it's popping out and wanting to be pressed. And if you're Scott Forstall, when they designed the Aqua, they would call it lickable. Okay, so now addressing more directly a mental model, there's a concept of what they call the action cycle, and the action cycle is the process a user's mind goes through when they try to do something into the real world, either through your interface or through a real object like a door. It starts with their mental model that gives them a sense of they think they know how it works, and then there's how the real world actually works. And in between those, there's what Norman identifies as the gulf of execution, which is kind of this hopefully small gap between how you think it works and how it actually works. And the gulf of evaluation is, again, this hopefully small gap between how the real world tells you what happened and what you expected to happen. And so as a designer, your job is to try to minimize those goals as much as possible. I feel like I'm missing. Okay, so one really useful thing in designing an interface is to take advantage of what's called an interface metaphor. And the idea of a metaphor is to design around things that the user is already familiar with, and allow those affordances to give your users clues as to how to use your interface. So all the built-in widgets, for example, all the buttons, all the sliders, all the switches, those, for the most part, are based off of real-world objects that we know how to flip a switch. We know how to drag some sort of a slider. We know how to press buttons in the real world. So those are examples of a metaphor because those leverage the fact that we know how to use real-world objects. And so if we know how to use a real-world object, we know how to use an interface element that resembles it. The caveat with metaphors, though, is if you've chosen a bad one or it's incomplete, the conceptual model you're going to generate is going to be totally wrong, and the user is not going to understand why it's not working if the metaphor doesn't make sense. So here are some more broader examples of a metaphor. An example of this Keynote, the presentation software I'm using, or PowerPoint if you're on Windows. These are like slide projectors, if anybody in this room even remembers what a slide projector is. But the idea is it's like a slide projector. But even that is almost not enough, because certainly Keynote can do a lot more than a slide projector can do. A slide projector just goes from picture to picture to picture to picture, whereas Keynote and PowerPoint can do animation and transitions and all these other fancy things that a slide projector can't. But it's a close enough metaphor that if we know how a slide projector works, we basically know how Keynote works. It allows you to go through a bunch of different screens of different things. One metaphor that's been around for ages, since Xerox developed it when they were developing the Xerox Star, is the notion of the desktop metaphor. The idea is that the desktop on your computer resembles a desktop in your office, that you have a bunch of files and folders on your desk. You have a trash can maybe underneath your desk. You have all these kind of things. And there are examples of fun UIs where they take that to the next level, and they have a UI that's the office. That you have an entire office with files and books and shelves and three-dimensional desks that are hard to use. But
Clippy. Microsoft Bob.
Yes. But it's a useful metaphor because we're familiar with how to mess with files and folders on our desk. So the idea that we have those similar things on our computer is not so bad. One issue, a small issue with that metaphor, at least on Mac, if you want to eject a disk on Mac, how do you do it? You drag it to the trash. If you had a desk, if sitting at your desk, if you want to remove a disk, would you really throw it in the trash can? Probably not. So it's not a perfect metaphor, but it seems to be good enough that it's lasted us 30 some odd years. So I think it's going to stick around for a while. Because it's a close enough metaphor to what we want. So as I mentioned, there can be some problems with the metaphor if you choose it incorrectly. One possibility is that the metaphor is limiting in that it's the metaphor isn't sufficiently descriptive of what your application can actually do. So if you could argue that the keynote as a slide projector is maybe a weak metaphor, because if they just think it's a slide projector, then they won't know about these cool things like animations and transitions and all these other fancy things that it can also do. So that might be limiting in some sense, because if they just assume that it works exactly like the metaphor, then they are missing out on a lot of other stuff that it can do. On the other hand, it might be too powerful. If you try to suggest that your computer desktop is your desktop, then there's things that you can do with your physical desktop that you can't do with your real one. And so the user will assume that they can do it because it would appear to match the metaphor, and then they try to do it and they can't because it's not actually part of your application. And so those are both kind of problematic. The last one is that the metaphor could be just mismatched. It could just not really map nicely onto what actually is going on. And so they'll think they know how it works, but they're actually doing something not really different. I meant to have examples for those, but whatever. Do you have an example?
An example of, don't take it too far. QuickTime 4, I don't know if anybody's ever seen this, was like if you search QuickTime 4 bad UI, you'll find an article that tears apart that program's just disastrousness. They decided to make it look like an actual physical device. So there's a little knob here that you can drag up and down in increments with your mouse to change the volume. The interface is like...
Which is an awful way to adjust the volume.
Yeah, it's like taken to the extreme, so too much of a good thing.
Yeah, so that might be a metaphor that's too powerful. Or just mismatched. So some guidelines for a good metaphor. What makes a good metaphor? A good metaphor is a metaphor that makes important the things that are actually essential and part of your application, and really disregards things that aren't part of the metaphor that your application can't do. So striking a balance between what you can actually do and what it can't do is kind of the importance in choosing your metaphor. Okay, so my last sort of section here is about how to design for error, in particular how to design for human error, because humans are not perfect. And well, maybe Glenn's perfect, but not everybody else. So Norman identifies two kinds of errors. One he calls slips, and the other he calls mistakes. Slips, basically, as he puts it, are what our brain does when we are not really paying attention, and mistakes are what happens when we consciously misunderstand something. And so mistakes, you just have to design your interface well and hope that they understand how it works. If somebody just gets it in their brain that your application works one way and they keep trying it and it doesn't work, then there's not a lot you can do about that. Slips are something that are really hard for users to detect because we're often unaware that we're doing them. Norman gives an example of a guy who comes home, takes off his socks, and accidentally throws them in the toilet because he mistook it for the laundry bin. So it's just your brain kind of gets distracted sometimes, and so those are really hard to spot because you don't really notice them until it's too late. So on a computer, this might be accidentally pressing the delete key when you're deleting the file. So slips are the sorts of things where you often might want to double check that the user is doing what they want to do. Yeah, and I'm not going to go into any more detail about them, but Norman actually goes even further and just details like 5 different kinds of slips and offers alternatives to how you can prevent those different kinds of slips. One popular thing that happens a lot that causes a lot of slips is the notion of a mode, and the mode is a mode is when you have the same action in different situations has a different effect. How many people have been burned by Microsoft Word's overtype setting? Where there's a little button that you press that rather than inserting characters at the cursor point, it types over your existing text. That's an example of a mode where you're typing, the typing's the same, but the effect is different based on the state of the switch. Caps lock is a mode. How many people have yelled on the internet on accident because they typed an entire sentence in caps lock because they didn't realize their caps lock key was on? Caps lock is another example of a mode. And so modes can be nice, especially if you have more things to do than you have controls. Modes are nice for that, in that it allows you to do twice as many things if you have multiple modes. The problem with modes is that users have to remember they're in the mode. If you turn on overtype and then forget to turn it off and continue to overtype, you did something you didn't probably want to do. And so modes are often the cause of a lot of errors because users will forget that they're in a mode. An alternative that I think Norman offers, he calls them quasi-modes, where they're modes, but they require some kind of conscious action to maintain. So an example, instead of holding down the caps lock key to type a bunch of characters in uppercase, if you hold down the shift key, then all the time that you're typing those capital letters, you know that you're typing capital letters because you feel that muscle tension of you holding down the shift key. Things like pull-down menus require you to have the mouse button held down. So again, there's that muscle tension of you pressing down all the time until you let go to remember that you're still in this pull-down menu. So if you think you might need modes, it's advisable to try to find a way to use some kind of quasi-mode, so that way the user can remember that they're in the mode. Otherwise, they will lose track of it, almost guaranteed. Okay, so there is a lot more about user interface design. This is kind of some of the highlights that I found when I took it last spring. The wiki from last spring, this is the one I borrowed the slides from. There's obviously a wiki from last semester as well. And that's a great resource if you want more detail about some of these different principles and tricks and tools. And also, The Design of Everyday Things is really an excellent book. So I really enjoyed it a lot. Okay, so that's all I have. We're gonna switch to Glenn, who's gonna talk a little bit about debugging.
While I set this up, do you want to talk about turn your QuickTime off too? Talk about why this is even important, especially for Apple products.
Put him on the spot here,
Do
Glenn.
eight things at the same time. Well, just why the Apple and human interface guidelines exist.
Yeah, so we'll talk about this a little bit more later, but Apple has a rather intensive guide for Mac and for iOS called the Human Interface Guidelines that gives very specific rules about how far apart different buttons need to be and different widgets need to be, and how to use different kinds of elements in their user interface. The reason that's useful is as long as everybody more or less follows these design rules, then users don't have to be retrained in every single application because, oh, this borrows all the same elements that are everywhere in OS X. So that way you can just, okay, I know how a button works in this one application, so therefore I know how a button works in every OS X application. And in fact, I know how this slider works, I know how it works everywhere. And as long as everybody follows these rules, then we know how everything works. Is that kind of what you were getting at?
Yeah. Let's get started with this.
Good.
Okay. Whoa. Something's messed up. So I think this thing freaked out when it got to one man and make sure that the text goes slow. Oh, hello. Okay, let's do a really quick log out one back in.
Does anybody have any questions about that about user interface design while we're waiting for Glenn to get ready? Any questions about Xcode or memory management or how to call messages? Man, you guys are amazing.
This thing is really freaking out. Whatever. So I'll make this quick, but hopefully even for hardcore debuggers, this will be helpful. Most of this stuff is going to be done in. I'm sorry. Try. I don't know. It's still acting really strangely. I think I probably need to restart, but I'm not going to. Even Spotlight isn't happy. I think I started it up. I think I started up in safe mode. So there you go. Yes. So even, and especially if you took this last semester, and I said these are some of the more hardcore debugging techniques, you'll recognize some of the earlier ones. Now you can practice with the hardcore techniques. So this is mostly going to be, I'm going to demo on Xcode 4. They're very similar in most ways. The user interface is about the biggest change. In Xcode 3, there's a separate debugger window. In Xcode 4, it's all integrated. There's some pretty large functional changes going on under the hood, and this is a table of them. This is also up on the website, or will be up on the website. Like I said, the integrated debugger window for Xcode 4 and the debugger window, the separate debugger window for Xcode 3. There's also a system utility called guard malloc that will put your code and put your data segments into privileged memory. So writing over the edge of it should result in an exception, and I'll demo that in a second. Unfortunately, there's some limitations to that that I'll also talk about. In Xcode 3, use a separate application, instruments, to check for what are called zombie objects. Those are objects that you've released and that have been deallocated, but you're still sending messages to. There's a way that you can tell the memory manager to not actually deallocate, not actually throw away objects, but mark them as being deallocated, and then there's stub code that's injected, that whenever you try and send a message to it, instead it logs to the debugger console that you are trying to send a message to an object that you have freed. In Xcode 4, it's integrated, and I'll show you a demonstration of that as well. In Xcode 3, this is a big user interface change actually. In Xcode 3, there is run, which is run without breakpoints and not using the debugger, and there's run and debug. In Xcode 4, they get rid of that, thankfully, because that's always been a really big source of confusion. What I always did was just counted on the keyboard equivalents, Command R to run, Command Y to debug. You'll see that they've shifted a bit in Xcode 4. So now Command R always runs always, and Command Y toggles breakpoints on and off. And I'll show you why that's important in a second. And then Xcode 3 has separate tools, especially for testing and optimization. For example, Shark, one of my favorite tools ever. And we're going to talk a lot more about that later on down the road when we talk about optimization and fine-tuning your applications. And then Xcode 4 introduces the static analyzer, actually LLVM, Objective-C2, and the new LLVM presents this new static analyzer, and I'll show you an example of using that as well. So, who's heard of assert? Who's used assert? Who uses assert all the time? Everybody's hand should be up at this point. Everybody. The assert is like one of your biggest friends, and if you're not using it and abusing it, you're missing out on a huge debugging tool, huge debugging aid. Asserts are very simple. Asserts basically evaluate an expression. If the expression turns out to be false, it throws an error. Either it raises an exception in C, it generates a message and just does a sys exit, In Objective-C, you'll see there's a couple of different ways that you can use assert. They have some macros, and they're prettier and log out to the console. But the bottom line is that the functionality is still the same across. The assert functionality is the same no matter what type of assertion checking you're using. It's evaluate an expression. If it's false, break into the debugger or print out a diagnostic message. Why is this helpful? Who uses assert? Why is that helpful? Yes.
Yes, so that's some incorrect data. Rather than getting some incorrect or garbage value that screws up the program data, the program stops at the right time.
Exactly. So it's very useful, incredibly useful for input checking, and that's input checking on your API. If you have a function and it takes 4 pointers, the very first piece of code that you should write when you write that function is assert that the first one's not null, assert that the second one's not null, assert that the third one's not null, assert that the fourth one's not null, if they're not supposed to be null. Here's what's really great about assertion checking. When you set a flag, the ndebug flag, it's all uppercase. Actually, I'm sorry, I should be on the next slide. This is a breakdown of the different pieces that we're going to talk about. If you set this flag ndebug, they all go away. Assert's always done as a macro. Always in C done as a macro. They've got assertions in Java and they've got assertions in Python. Sometimes they're macro, sometimes they're done as a function. There's a little bit of overhead in C and Objective-C and C++. When you define ndebug, asserts go away. They disappear. They're defined as null macros. So there's no performance hit whatsoever. So there's really no good reason not to use them. They also help document your API. If you're taking 4 input values, four pointer parameters to a function, and you have 3 assertion checkings on the first 3, and the second one is this pointer is not null, or if it is null, then pointer number 3 is null, is an excellent way to self-document and show that this is what you're expecting of your API. Commonly this is used within just a big macro, a big like overarching debug flag. That's what I tend to use, is a debug flag that turns assertions on, turns on a whole bunch of other error checking code, turns on a bunch of diagnostic messages, and then I use the debug flag to just flip this ndebug on and off. It's really, really handy, really, really convenient, and there's zero overhead in your runtime code. It should never contain an assignment. It should always just be a regular expression, an evaluated expression. Why shouldn't it contain an assignment?
Assignment always equals true.
Not necessarily. X equals 0. It's going to evaluate to false. Why is that? Regardless of how that evaluates, why is having an assignment and assertion macro hint a bad thing?
What if you use ndebug?
Turn ndebug on, macro goes away, the assignment goes away. Your code acts differently, right? So you change the flow of logic. So it should always be an expression that's just checking or results in a Boolean value that has no side effects. It's also really common to sanity check outputs too. So you've got a function, you've got some inputs, you run some code, and then at the very end you show you've got you can double check to make sure that the values that you're returning are sane values. Yes, you wrote the code. Yes, you write perfect code the first time. But other people who might be using your APIs and using your code might send bad inputs or send edge case inputs in, and you, unfortunately, without any foresight, generate some invalid return values. If you catch it right there, it's very obvious where it happens, as opposed to bubbling up and propagating through the rest of the code before something breaks. So assertions, super, super simple. This for a couple of these other parts too. So, for instance, character, my cool string equals R6, blah, blah, blah. Insert cool string. Before we use it, my cool string yeah, I started it as a just a C project. So a lot of times you'll see people error checking code like this, which is a really good it's good behavior to get into. Like you'll see this in the init boilerplate code, right? Checking to make sure that the init routine, the super, that your parent initialization and allocation, that all works correctly. You should be doing that. But if there's some function that you don't have control over, and you're not explicitly checking for null, you're not explicitly checking for garbage values, you're just setting yourself up to end up with really subtle bugs later on. They're really hard to track down. So it's never a bad idea to constantly check and to double check your input and output parameters. If that's all you do at the very minimum, that'll get you way ahead in the game. Here's a good example of doing that. Let's say we've got this function called mymalloc. We could take an integer size, right? Which is not a great idea in the first place, right? It should be a size t and unsigned. So what we're going to do is, let's say we have to, because it's expecting an integer. That's what our API has given us. So let's double check and make sure that size is greater than 0 and size is less than int. We won't include that header. Let's just make sure that the size is greater than 0. So I usually forget to leave this out because I always put this in, it's the first line in my precompiled headers, always, all the time, is assert.h. So this actually isn't going to show us anything because this assertion isn't going to fail because I'm passing in a size that's greater than 0. Got a whole bunch of code. Setting X, you got a whole bunch of code, and this is a perfect example of double checking inputs, and something that you might miss if this was layer upon layer upon layer. It's a really simple check. So you run it. When you run it, you'll get, this is the C output. I'm going to let you guys explore with and I believe there's some pieces of the lab that do this, explore some of the Objective-C assertion macros, and I'll show you a list of those in a second here. But here's what the output of an assertion failure looks like. It basically takes exactly what's within the assert in the assert macro between the parens and turns that into a string. It says this failed, size is equal to 0. Here's the function that it was in, the line number, and the file that it was in. And if I define, this is probably going to crash things, but if I define ndebug, here's it not being caught, right? So I tried to malloc a negative integer. Fine, malloc says, great, okay, whatever. So you're passing in an integer. And I get a bad access down here, an abort down here, right? Much easier to tell if I've just got some really simple assertion checking. And this ndebug definition turns all of the assertion macros off. So there's 0 performance hit. Super helpful. So NSLog, yes.
So what was the one you wrote in front of
The one here, I just define it as a value. I mean, sometimes some libraries do if ndebug, and some libraries do if def ndebug. So I just take the bottom line of it's going to define it as a value. So either way will work. Who uses NSLog? Who writes a ton of printfs in their C code and C++ code? Yeah, so NSLog is your equivalent in Objective-C, is your equivalent to a printf, although there's some really convenient things about NSLog. Who's used NSLog, or have you seen it in the labs? Should have seen it in the last memory management lab. So the one really nice thing about NSLog is that it also spits out to the console too, and gives you a timestamp, which is really, really helpful. So we're going to say here if the size, this is C, let's see what happens. I think it's just it's not a Cocoa program. Let's get it. So NSLog is, it's functionally looks very, very similar to printf. NSLog, this is when the application finished launching. Yeah, it's not a whole lot of utility in the sample program here, but so. One thing you'll notice right off the bat, you'll get a warning if you try and just put a regular C string in there. The warning got covered up here because I ran it and I got an exec abort here. It doesn't take a C string. NSLog takes NS strings, takes objects. So what is this? How do I change this into an NS string constant? @ sign. So here's what the output looks like. Unfortunately, this window's super small. It's not. It actually goes on one line. Here's the timestamp, the function that was called, and then the string that you're printing out. If you look in the console application, here's what's so. Why is that not working? Here is Here's one of the primary reasons for actually having this around in the first place and not just using printf, because if you have a application, a GUI that doesn't have any kind of text output or text display, it's often really helpful to still have diagnostic messages that you can still see while the program is running. So if you look here, right here, this is showing all the messages, but if you look right here, here's the NSLog printout that we just spit out. Unfortunately, I called the project NSLog. If you call whatever your project name is, whatever your application name is what's going to show up here. There we go, NS right here. So, like these are diagnostic messages that are coming from Xcode. If your application is called my cool application, it'll have the timestamp. My cool application, and then anything that you print out there. Here's what's also, here's one of the big benefits is you can You can pass it. You pass format specifiers, printf format specifiers, just like you would with printf. But there's a new one, and you learned about that. Objective C 1 or 2. What was? Do you remember what that was? I won't go through and demo that, but just as a reminder. The %at, right? Format specifier that's specific to NSLog doesn't exist in printf. It doesn't exist in most printf libraries. Calls an object description. Description is a message within every NS object. Typically, it comes back with class name : at memory address that's the description of your object. If you override this description and you return an NS string pointer, you're basically creating a toString for your class. Description is a message that you can override, or a method that you can override. Return back a string full of a whole bunch of information about your object, and when you NS log it like this, it'll call that and print that out. Really, really helpful. So guard-malloc is, it's in the debugging menu on Xcode 3. In Xcode 4, it's in the schemes. You can see the setting right here when you've got, like I'm going to test, I'm going to run it under debugging and under diagnostics here. Guard-malloc is right here, and just so I don't have to come back to it again, here's where you set zombie objects. You can turn checking for zombie objects on and off. These are a pretty big performance hit. So you want to use this under your testing, under your debugging scheme, and not under your released code scheme. These are special libraries and code injections and stubs that do a lot of extra error checking to make sure that your code is stable and functioning correctly. Guard-malloc, like I said before, puts your code and data and everything into protected segments. They're 16 byte aligned just for the processor. So if you're off, if you run over or under a buffer by a couple of bytes, sometimes you'll get, sometimes it'll flag, sometimes it won't. It's gotten a lot better about it. You used to be able to almost all the time run over by a couple of bytes. It's gotten a lot better about automatically aligning the code and padding the code and the data out, so that it almost always catches a bad overwrite of memory. So if we let's turn guard-malloc on in our original program here, and we're going to allocate 256 bytes, and right at 256 we're gonna slap a space. Yeah. So when you have guard-malloc turned on, it spits out your project and the line number. It tells you ahead of time that it's running. That's why everything's going to be running very slowly. And it provides the warning message that sometimes it won't catch the underruns. Sometimes it's overruns just because of the way that the buffers are aligned. But it's still an incredibly useful tool when you are testing your code, especially if you're testing it across multiple runs. It'll almost always catch bad allocations. But like I said, you take a performance hit with it. So you don't want to do it with user interface testing, and you don't want to do it with you might have to figure out a different way to do it. If you're interested, I can show you how to do it in a really raw way, low-level way, without taking such a performance hit, but you lose some of the functionality. All right, so that is guard-malloc, and like I said, I can show you how to write Sentinel memory management so that you can perfectly catch 1 byte overrun and underruns. Breakpoints in the debugger. So helpful that every time I write an app, for every single function that I write, oh, now I've done it. For every single function that I write, my free string. First thing I should do? Assert what? The buffer's not null. Right? For every single function I write, I put a breakpoint in when I first write it. Always, always, always. All the time. Even my main. Put a breakpoint in. When you run this, make sure this other stuff stops back here. This is now, remember, this is Xcode 4. On Xcode 3, you have to switch to the debugger window, but it acts basically the same. The window layout is a little bit different, and where it prints out variables is a little bit different, but it's still the same concept. So when you run it, what? Oh, I didn't declare it. So as you're running, it'll stop. You'll see where it stops. Oh, by the way, sorry. In the gutter here on the left of where the code collapse gutter is, where you've got the line numbers, is where you set breakpoints. Click it once to turn it on. Click it again to disable it. It leaves the breakpoint there, but it won't stop there. That's really helpful if you want to go back and check code later. If you want to get rid of a breakpoint, just drag it off the bar. So you can see right now the program counter is sitting here at line 22. It's telling us that there's only one thread running. This Xcode is awesome at multi-threaded debugging. Xcode 4, I should say, is awesome at multi-threaded debugging. Incredibly helpful. So we're stopped in thread 1. Here's our function. That'll actually give us the full function stack if we're inside. Actually, I'll show you that in just a second. It didn't stop at the declaration because there was no code generated there. Down here on the left, here's all of the local variables. There's one argument, one argc that comes in, right? It's the name of the program. Clicking on any one of these and opening it up will show you the contents of the memory at that location, or try and show it to you as a natural value if it's an integer, say, like this argument C. These are arguments that have come in. These are local variables you've defined. You can also take a look at your global variables too. You can even look at register values inside of here if you so desire, which comes in really helpful. It comes in really handy for performance tuning, but we won't worry about that right now. So on the right-hand side here is output from your program, just like the console window. You can enter GDB commands right here. This is Xcode. Xcode's debugger is a graphic front end at GDB. That's its specialty and its power. You can enter any GDB commands that you want to in here, and it functions just like you would expect in GDB. Or you can use the graphic user interface Xcode for that. So it's super powerful. Single stepping controls down here in the debugging window in Xcode 3. They're up on the top. This is continue on until it hits the next breakpoint. This is step over the next instruction. So if it goes into a function, it'll step over that function by running it and then returning back to you. This is step in to a function. So for instance, when we get to my malloc here and we want to step in, we can go dive into the function and take a look at it. Here's our local variables size that's come in. Nothing really else except here's the call stack here. My malloc is what the current frame, and main was the calling frame. As you dive down into functions, that frame will build up. You can select any of these here, any of the frames, to see exactly where it jumped into the function. Also really helpful. You can see the variables. So if you stop way down in a function and something's been passed in incorrectly, all you have to do is click on an upper frame and take a look at the state of the variables at any point where your function was called. So now we're going to step out of the function, and there's our program counter that has come back, that is returned back. We'll see that we get, what did I do? out twice. So we step over here. Everything that's blue is what's changed since the last step you made. So if you have a breakpoint in a function and you run it, and then you run it again, and you run it, and you just keep hitting continue, you'll see exactly which variables change. Really, really helpful with an object. When you have an object with a ton of instance variables, you can see exactly which instance variables changed in between each time you took a step over in the code or you continued on to the next breakpoint. So here's the pointer that was returned. Other really super cool features about breakpoints, you can move them around in here. You can also set conditions. So if you right click and say edit breakpoint, we can actually set a conditional breakpoint, which basically says, okay, if the size is greater than 0, then I want it to continue on. Otherwise, if the size is less than or equal to 0, I want it to break. And you can issue other GDB commands if you want to. So now what I'll do is I'll stop it. If I run it, I'll see that continue. I'll see that it didn't stop there because size is 256. Let's change size to minus 256. Run it again. Continue. And it breaks here because size is less than or equal to 0. Really, really handy. Really, really helpful. There's all kinds of cool stuff you can do in here too. You can make it play a sound when it hits a breakpoint and not stop, which is really helpful if you have some process that you need, especially a process that's timed. It's really helpful to be able to have different sounds playing. You'll find it really helpful if you can figure out how to use it. It actually becomes it's really, really super handy where you can play like different sounds as different portions of your code is hit, so you don't have to stop. You don't have to interrupt the flow of your application. So clicking them, again, click once to the left of the code folding gutter to enable them or to turn one on, drag it off the bar to remove the breakpoint, click it once to disable it. What I said also about the command key equivalence, run is always run in Xcode 4. Hitting Command Y is the same as the shortcut here for disabling all of the breakpoints. And you can see all of the breakpoints now on the left-hand side are disabled. Watching variables is also incredibly helpful. Let's say we want to know when this X has changed. X equals 512. We do a bunch of code. X is so we have a bunch of code in here, and then we want to see where we notice that we make this call to mymalloc, and either our assertion fails, or the breakpoint gets toggled, or the breakpoint it stops at the breakpoint. So we want to know when X changes in our code. So what we'll do is we'll re-enable breakpoints. We do run, and then if you can see the local variables in the current stack frame, you can right click on the variable itself and you can do watch X. Watch X means break every time X changes. Super helpful, incredibly helpful when it comes to global variables. You're relying on a global variable and a global variable changes somewhere and it's screwing up the rest of your code flow. You just watch that global variable. Anytime that global variable changes, anytime that variable changes, the debugger will break. Really, really helpful. You can also take a look inside of memory from here. That's a little bit harder, a little more hardcore debugging, but really helpful if you need to look inside of a raw memory buffer. All this documentation is in the Xcode documentation, by the way. So you can, even inside of here, let's say you've noticed, oh, here I am in main, and oh, this is going to call my malloc and x's minus 256. Well, let's make it 256 for right now. And we're going to we'll step over it, and yeah, cool, worked. We got a pointer, 256 bytes long. Now we can go in and change the code, because you don't have to stop. You don't have to stop, edit, recompile, and rerun. You can modify variables right here in the debugger while it's running. You can even change the program counter. This is all stuff that you're not normally going to be doing, but it's really, really helpful if you've got, say you find a small bug, and let's say you've gone through like 50 user interface items to get to a certain state of your program, and you find something like this. There's a problem with your code, and you don't want to stop, fix it, recompile, and go all the way back through all those user interface elements. So you tweak it right here. And let's say, oh, I need this buffer to be, this is going to overrun the buffer, so I actually need it to be one more. So what we'll do is we'll rerun this line again. Grab the program counter, drag it up to there. There's where the program is stopped now. We'll make this 257 instead of 256. Step over, come out, step over. Cool. And we didn't get an exception from it. These links are not active in this document. Apple has an awesome debugging and analyzing your code document. We're going to talk about analyzing code later on. We talk about performance tuning and enhancements. And then there's also a whole section on iOS debugging. Running it under the simulator, running it on the hardware, how you stop on the simulator, how you stop under hardware, look at variables, change variables, log things to the console. Did you have a question? Are you stretching? Stretching. Okay. Questions? Cool. So that was just kind of an overview of some of the debugging techniques, especially that I use. And there's a lot more. Apple provides a lot more, but I think those are probably the most powerful and the most helpful ones. Some of you noticed already that if you raise your hand and I come over and you say this doesn't work, I'll ask you why it doesn't work. And if you say I don't know, that tells me almost immediately that you haven't even opened up the debugger yet. So get comfortable with it. Your debugger is your friend. And helpful macros like assert are also your friend. Trust them and use them because they're there for a reason and they're really super helpful. Yes?
So, is that the one where you can change the program counter?
Yeah.
Is there any way to edit code on the fly?
So in Xcode 3, there's fix and continue. I've never had really super good luck with that. Something usually ends up crossing a page boundary, and it says, I can't do it, it doesn't work. Or values really weird values start happening with memory where you start getting overlaps and things like that. I don't even know if it exists in Xcode 4 anymore because it was so unreliable. Even if it does exist, I would recommend not using it. It can get you thinking in a mode of, okay, I'm fixing it live, like right here. If I have found that minus 256, and I change it and say, okay, fix and continue, and say, okay, up there, I'm done. I fixed my bug. Not really, right? You need to run it again to make sure that you fixed it, right? So this is actually better than fix and continue, I think, where you can tweak memory, you can change the program counter if you need to, but it only means that you're going to allow to continue running, but you still need to go back and debug it. So you need to make sure that it's fixed.
You can drag the program counter back. Can you drag the program counter so it stays?
I'm almost positive that you can. Yeah, so if we saw this and actually I know you can because I've done this before. Oops. So we're here and we say, oh, we want to leave X as 512. We don't want to have make it 256. So we'll skip it. Yes.
Wait, I didn't really understand
understand what guard mallet does. Like, what is there a specific situation when you should use it?
It's I'll tell you how I use it, because everybody uses it a little bit differently. I use it. I'll compile. I'll edit some code, compile it. I'll set my breakpoints, single step through it. Once I'm pretty sure that my code is working correctly, I'll turn guard malloc and a whole bunch of other guard software on, and make sure that all the asserts and all my warning levels are set at the highest levels, and like do a live run with all of these checks going at the same time. If I find a problem, then I step back, then I fall back. I turn that back off again, and it's just a simple. Actually, with the schemes now, it's just a one-click menu option. And I switch back, and I go back into my edit, compile, debug mode until I'm sure that I've got it
Or are
set
you
back.
asking specifically what guard malloc is for?
Yeah.
So guard malloc is for checking. It's an automated way to check for memory, for invalid memory access that isn't caught by a regular like a SIG exec aboard. It does more.
The common case is if you have an array of characters and then you write past the end of the array, the regular pointer checking logic of C isn't going to catch that most of the time, but guard malloc in theory would.
Right. So if you have two character buffers of size 256 that are sitting on the stack right next to each other, and you overwrite the first one, you're not going to catch it in the second. You're not going to catch that override in the second one, right? You will with guard malloc because it puts everything on it in its own buffer, and it puts it on boundaries, in page boundaries, so that overwriting off either end results in a privilege exception, privilege memory access exception. It's not a crutch, but it's a really useful tool. Yeah.
Can you also use it to check for bus errors?
What type of bus error?
So like if you like any kind of misalignment of your memory addresses.
I'm not sure if you can do that.
Yeah. There's
Like in C you can access specific bytes.
right.
And if I want to do that, but I want to make sure that I'm not like going to the third byte. Like if I want to go
Unaligned memory accesses.
Yeah.
We can talk about this offline because you write code preventatively for that. So you write code in macros that always align your pointers on word or long word or double long word boundaries. And so you do that. So you do it ahead of time because guard malloc, guard malloc, you're hoping that it's going to check 1 byte accesses off of either end, but you still want it to allow it to you still want you to allow to write to a single byte anywhere in a buffer without having to trip. Anybody else? Cool.
Okay, I know that was long, but it's useful. I think being able to use a debugger correctly is really a useful skill. The lab is kind of not that long. It's just basically to get you guys start thinking about your application for your final project a little bit. Just do a little bit of mock-up of your just do a first mock-up of your user interface. So that's not a big deal. You don't have very much time for it. Michael David said that he put I asked him to put 6 people on the wait list for 198 into the class, and he said he did that. So I think there's only like 2 or 3 people left on the wait list, or once it gets processed, there will only be a couple people. I have attendance sheets again, so just make sure to come up and check that. Hopefully we have. Yeah.
so for the projects, are we supposed to work individually or do we work in like
That's a good point. I should talk about that. The projects, we allow you to do them either individually or in pairs. We tend to recommend very strongly to do them in pairs. We think that projects turn out better if people are working in pairs. We won't make you, but we recommend it. So it's either individual or in pairs. Anybody else? Okay, thanks.